Let's put an r to the power n here. There was an r to the power n here that I missed. So what is h of z here? Are you guys working on it? Aniket?
Yes, sir.
Anik?
Yes, sir, I'm working.
Akshat? You disappeared last time. Towards the end. That is if you are hearing it today. Akshat? Abhisht? Abhikya?
Yes, sir, I'm doing.
Giridhar?
Yes, sir, I'm trying.
Okay. Madhusudan Agarwal? Madhusudan? Rekha?
Yes, sir, I'm trying.
Lokesh, that is.
Lokesh.
Yeah, Rishabh.
Yes, sir, I'm doing.
Okay, tell me what have you tried so far? So what is HZ here? Anybody? How do we calculate HZ? Come on. You can at least start with that.
Imaginary part of impulse, I think.
Huh? Oh,
Breaking sign into exponential terms and then
yeah, so this first of all,
n equal to 0 from 0 to
we
infinity.
can, because of the
Causal.
unit step function, basically, we can write this as going from 0 to infinity, z to the power minus n, right? R to the power n, sine n plus 1 theta by sine theta. Okay? So now we can we break the sine n plus 1 theta into using the Euler's theorem. What is sine n plus 1 theta in terms of exponentials?
1 by 2g into e to the power n plus 1 theta g minus e to the power minus n plus 1 theta g.
Theta j e to the power n plus 1 theta j.
Yes, sir.
Minus e to the power n plus minus n plus 1 theta j. Right? Is that okay? Uh, so now can you extend this? So this becomes, all of this becomes exponentials. I mean, z to the power minus n, r to the power n, then e to the power n theta g. Summing from 0 to infinity. What do we need? Guys, I won't do it. Uh, you have to participate, please. Shravanti. Shrey.
Yes, sir.
Surya has given an answer, but how do you get to that answer?
Sir, I did in similar process, but not this. So
Okay, what?
I did in some other process, sir.
What process?
I took sine n plus 1 theta as imaginary part of e power j n plus 1 theta. And so I calculated like that.
Imaginary part of j n plus 1 e to the power j n plus 1 theta. Okay. I mean, that is what this sine n plus 1 theta is, isn't it?
Yes, sir. So we get a GP in n, a geometric progression kind of thing in n.
How do you get geometric progression? Is you get it? How do you get that with imaginary part?
I mean, since sin n plus 1 theta is imaginary part of that, so we have to find so h of z is imaginary part of the whole thing when sin n plus 1 theta is substituted by e power j n plus 1 theta.
Well, I mean, you would get the same thing in the. I mean, you are doing the same thing, but how can you write that imaginary part of sine e to the power j n plus 1 theta into the factor of the GP is what I was wondering. Well, here also you will get the same thing, and you would get to the answer. The sine theta would cancel out, and you would get basically what you were getting. What was it? 2r cos n plus 1 theta, is it? N won't be there. What did you get? 2r cos theta. Yeah. Two rz cos theta plus r square z square, and you have a 1 here, right, Surya?
Yes, sir. That's what I got.
Yeah, so where are the poles of this? Alisha? Akash? Shubhrajit? Nandram? Dasari? It depends upon the angle theta. Yeah, I mean, for some theta, where exactly are the poles here? So for some theta, I mean, what would the pole
So r into e to the power plus minus j theta.
r into e to the power plus minus j theta? Those are the locations of the pole. So where are they in this plot? Let us remove the ones that we drew. Let us say theta is 30 degrees, pi by 6. Okay, what about the ROC? That was the first thing that we should have discussed.
Sir, I think it was not r square z square. It was r square z to the power minus 2.
And this is also z to
Yes,
the power minus
minus
1. Yeah.
Yes, sir.
Yeah.
Yes.
So coming to ROC now. Is the right-sided signal. So what should be the ROC like? This is a causal signal.
not z greater than r.
Rz greater than R, and so for the Fourier transform, the DTFT or the frequency response to exist, R must be less than 1.
Yes.
Yeah. So then it should be inside this, and so how much inside? That is basically up to R, right? So let us say this is the length R. So the poles are basically going to be on this circle. Again from the properties, and this is the angle theta. And so in order to compute the or understand the frequency response, we look at the product of the magnitude of these two vectors, and we divide by that, a reciprocal of that, if we since the denominator is essentially 1 or z squared, so it is there are two zeros at the origin, and both are going to have unit magnitude. So it is 1 over magnitude of the product of the magnitude of these two vectors. So what should it be like? Any idea? The frequency response of a system whose impulse response is given by this function. Now, this is the second order system as we see here. So we have two poles. So what does the frequency response look like? What happens if we compare with 0 and pi? Let us say. Come on. These are easy things you should say. Come on, say. So,
At
yeah,
0 it will be maximum and at pi it will be minimum.
at 0 it will be maximum and at pi it will be minimum. Is it necessary that, I
I
mean,
mean, at 0 it will be more than pi.
yeah, at 0 it will be more than pi because these are shorter, but where will it be maximum? I mean, is it necessary that it will be maximum at 0? That is my question. I mean, does it have to be a low pass filter? And what will that depend on? Aniket? Onik? Shubhadeep? Alicia is not here. Last time I didn't hear you. Akash also. Plus and minus theta. Which at angle theta? I mean, and 2 pi minus theta. So you're saying that it is going to be the largest when this vector is here and this vector is here, right? I mean, that we can say from by looking at this equation here. Okay. Geometrically also we can say that if we think a little bit about it, that is where I mean, it is not trivial, but geometrically also we can prove that it is going to be maximum here. The point I was trying to make is that without even this transfer function, just from the pole zero plot, there is a geometric way of determining the frequency response. That is the main message that I was trying to give. And yes, with some geometrical analysis, you will be able to show that the maximum will be at theta. Okay. And this, of course, will, if we analyze this, we can directly say it will be at theta. So this also, this kind of way to interpret the frequency response will come in handy as we go on. So didn't you guys do this geometric way of determining impulse response from the pole zero plot in signals and systems? Now tell me the truth.
No, sir.
No, sir.
Really? Okay. Um, so how about this, that here I take a short break. Is that okay? Maybe 5 minutes, and then we start again at it's little past 9.
Okay, sir.
Okay. This is the first time you are seeing the prof asking for a break. So as I was saying, we can do with one meeting link. I know how people are going to be. So the other class students, other link students, Nandaram and Akash, you can join the other one. Okay, so this is pretty much what we had to discuss in terms of the revision of signals and systems part. The next part of the revision is basically random signals. Do you want to do the random signals revision, which will take one lecture or maybe 2 lectures now or later? We will discuss random processes, stationarity, white sense stationarity, ergodicity, and then basically build up to the Wiener-Khinchin theorem. Any inputs on that? Any thoughts on that?
Sir, we haven't done all those.
I thought you did the Wiener-Khinchin theorem, right?
Yes, just the theorem, but we did not learn the random process.
So did you guys do what is it called, statistics and stochastic processes course? Electronics students? I mean, mostly it is electronic students here. I mean, there are a few electrical engineering students. Shubhadeep?
Yes, sir, we did. We did, but ergodicity and all this white sense stationary, these concepts we don't know. We did a bit of random process, but there was we did a few.
No, I'm saying there is a maths course, stochastic processes.
Yes, we had that course. We had that course.
Okay. And there also these things were not covered. Okay. That's strange. So is it that you are saying that we covered that part now as opposed to in the middle of the semester? Go into estimation of spectrum and so on.
So if we do not do the random process part now, what part we would start?
We will go into basically discrete Fourier series, discrete Fourier transform, and then filters design. And if we do the random process part, we will complete all the revision as in the brush up, which is 1 week is supposed to be for that. As per the syllabus, I'm supposed to do the revision, and we complete the revision and then get into the whole. With this tutorial tomorrow, we complete the process and then start from Monday with the actual, I mean, the continuation part, like whatever is the starting point of DSP. So we will do first discrete Fourier series, discrete Fourier transform, then calculating discrete Fourier transform, algorithms for calculating it, FFT, then filter design, and so on. Surya, Aniket, Anik, Vishwashu, Shubhadeep, what are your thoughts? Lokesh,
Sir, I think we can do the revision later.
you can do the revision later. Anybody else?
Yes,
Is
sir,
that
later part.
So
Shubhan
yes,
also
that's
says
fine.
later? Huh?
So yes, that's fine.
That's fine. Okay. So let us go to the discrete Fourier series. Um, let me see. Again, someone has joined. So let's say, so you did the Fourier series where you had xt as a periodic signal. That means xt equals x t plus n into capital T. And so this is the period of the signal, and we know that we can represent a periodic signal xt um, with the fundamental frequency, fundamental exponential with the frequency of the period of the signal and its harmonic, and we need infinite number of harmonics of the fundamental frequency to represent this periodic signal completely. When we consider, let's say, x tilde n discrete time Fourier series, discrete time periodic signal, sorry, um, that is, this is equal to x tilde n minus k capital N. Then also we can represent x tilde n in terms of a discrete Fourier series. So how do we write that discrete Fourier series? Let me actually, because k will be used for frequency, let us write this as r. So we know that we can write this x tilde n as a weighted sum of the harmonics of the fundamental k equal to 0 to capital N minus 1 x k e to the power j 2 pi by capital N into k. So we are saying that we can write the periodic signal x tilde n with the scaling and sum of all the harmonics possible of the fundamental in this discrete case.
So shouldn't there be a small n? E to the power of j 2 pi by capital N k is small n, I think.
Nk. This is capital N, where capital N is the period of the periodic signal. So how do we determine x tilde k? That is the Fourier coefficients in the discrete case. So in order to represent the signal in the frequency domain, we need to be able to calculate this x tilde k. How do we do that?
So x tilde n into e to the power minus j 2 pi by capital N nk summation over all n from 0 to n minus 1.
Multiplied by
Nk summation over all n equal to 0 to capital N minus 1.
actually, if we use this k, we lose generality, isn't it?
I didn't understand what.
I mean, can we use the same k as here on the left hand side?
So ultimately it is going to be a function of k, right?
Yeah, it will be a function of k. Same n. Is that okay?
Okay, we can use, instead of n, we can use something else.
Instead of n, we can use something. This n is here, right? So we
Yes,
need the
and
little n. Can we use the same k is the question.
We are finding the value of x tilde k, so it depends on which value of x tilde k we are finding out.
So we cannot use that k, right? So this has to be some other integer, let's say r. And this we sum over 0 to capital N minus 1, which is equal to 1 over capital N, or rather we have to do the summation first. Summation n equals 0 to capital N minus 1, 1 by n summation k equals 0 to capital N minus 1 x tilde k e to the power j 2 pi by capital N, and then we have k minus r into n. Now do you see why we cannot use the k? Who was it? Why?
Yes, yes.
Okay. So now how do we go about the business? Of course, change the order of the summation. So here we have the expression n equals 0 to capital N minus 1. This is 0. X tilde n, the periodic signal, e to the power minus j 2 pi by n. This is the fundamental frequency into n r. This is equal to k equals 0 to capital N minus 1 x tilde k summation n equals 0 to capital N minus 1 e to the power j 2 pi by capital N into k minus n into n. This is not minus. So what is this sum? There's an n here. Oh, and there is a 1 by n. Let us write it out. Just simply the inside summation e to the power j 2 pi by n into k minus r into n equals 0 to capital N minus 1. So what happens for K minus R into N is equal to, or rather it's not equal to, M times capital N. That is, this is not an integer multiple of capital N.
Zero.
Why is it 0?
It will be full circle with opposite vector.
It will be full circle with opposing vectors that will cancel each other. And when K minus R into N is an integer multiple of capital N,
So K minus R.
It
What?
will be 1.
So
why will this sum be 1?
It will be ends.
Sir, 1 plus 1 plus 1.
I'm sorry? It will be simply capital N, right?
Yes,
This is
yes.
1 plus 1 plus 1 up to capital N times. So what do we get then? This is equal to 1 or 0, where it is 1 when K minus R is an integer multiple of capital N and is equal to 0 otherwise. So what do we get as the representation of, so the right hand side here becomes simply x tilde k, right? When we sum across n equals 0 to capital N minus 1 for whatever n or r we have. And so summation e to the power, sorry. Let us also consider this case. So, and for r equal to k, what happens? Obviously, that is also 1, right? It is this m as 0. So we can write after the sum for any k, this x tilde k, when k equals to r, we can write that x tilde k or the Fourier series coefficients as n equals 0 to capital N minus 1 x tilde n e to the power minus j 2 pi by capital N into k. So we introduce this notation here that no, not n, kn rather. We introduce this notation here where we represent this as w kn by, this is not by, and that is the superscript, and this is the subscript capital N. I mean, this is actually not superscript, it is actually the power. So W n, this suffix n, represents this e to the power minus j 2 pi by capital N. Okay, so our x tilde k, now on we will represent it as n equals 0 to capital N minus 1 x tilde n w or k n and capital N. So this is the discrete Fourier series. Now, what does this physically represent in terms of? So first of all, this xk is periodic, right? So if we go on increasing k beyond from capital N, so they basically w 0 capital N is equal to w n capital N, right? And w1 capital N is w n plus 1 capital N, and so on. That is, we already know that. So what does this physically represent? This w kn by capital N, if we think of what we were discussing earlier in the z plane, what does this represent? I need you to interact. So are we sampling that unit circle in some way? Sorry, this is minus kn. Already pointed that out. No, sorry. This is x. This is uh, no. This will have the minus, right? It's about minus j 2 pi. There's no minus here. The minus would be there. Delta here. So what does this w represent? Come on. Anybody? No, sorry, this is W, this we are replacing, sorry. The minus is included in this W, so yeah, that is Kn. If you do not interact, I am not going to go forward.
So W is constant, right?
W is constant for a particular Kn and capital N. So for the different values of K, what does it represent? I'm talking about this particular term here, this WKN, capital N. For the different values of K, what is it representing?
Discrete points on the unit circle.
So they are, and what is the N then, the implication of N?
The
Total length
separation
of
between the
point.
points.
Hmm?
Separation between the points.
Well, I mean, 2 pi by capital N is the um, 2 pi by capital N is the fundamental frequency. N times that is going to be the nth harmonic, and or rather, I mean, if we take K times that, it is the kth harmonic, and then N is simply an integer that multiplies it over the circle. So it depends on what that particular value of N is, as it varies from 0 to capital N minus 1. So the WKN is basically representing, it is for minus J, so representing the samples on the unit circle over there. And as we sum it, we are essentially multiplying by this capital N and scaling by the signal and summing over on the, I mean, basically for all the different angles there. Is that okay? Okay. So now let us say we have a unit impulse delta n that is repeating every capital N. So essentially we write this another periodic signal x tilde n equals to delta n minus r capital N, let's say. And we sum this for the r's going from minus infinity to infinity. So we have multiple samples. So it is basically an impulse at every capital N, and zeros on the other side. So this is the x tilde n, where one period is like this, let's say. So this is 0. In one period, it is delta n. So what is the Fourier series represented, discrete Fourier series representation of this signal? By simply using the previous what do we write it as? We have summation n equals 0 to capital N minus 1 x tilde n e to the power, or rather w k n.
It will be 1. X at k equals to 1.
I'm sorry? This is delta n, right? So we have
It will
only,
be delta n series another
Yes, it will be another delta n series.
it will be another delta n series.
in the frequency.
So it will be 1. So that means for any k, it is 1. It is
This
not,
one is also periodic, right? So
no, I'm not saying what you're saying. It will be another, that you are wrong, that it is periodic. So that just means that for any k, it is 1. And goes on. So the delta function with a period of capital N, the dot delta function, the unit discrete unit impulse with a period of capital N provides all the frequencies in 0 to 2 pi. Okay, for all the different frequencies. Now if we say that it is only a delta function and not periodic, let's say it is aperiodic, then what is the frequency domain representation?
DTFT.
This DTFT, I mean, how do we go from this discrete Fourier series xk to the DTFT?
N tends to infinity.
This capital N tends to infinity. And so what exactly happens in this process?
it becomes continuous.
Does it really become continuous? Does it fill up the entire frequency axis? Hello, I cannot hear you.
Discrete to
Aniket, I cannot hear you at all. I mean, you're breaking up.
Delta functions.
I'm sorry, I did not hear you. Anyone else? I think, or Aniket, you can type if you want, or anyone else who wants to chip in here. So we want n going to infinity here. And that would be our way to get into from the Fourier series, discrete Fourier series, to the discrete time Fourier transform. That is, let us say we have now only the delta function, not function, the unit impulse here at n equals 0. So essentially what we are saying that if this is the case, from going from here to here, we make n tend to infinity. And I think, who was it? Someone, Surya. Surya said that now the k-axis becomes continuous. Does it really become continuous is my question. Is that entirely true?
So it is also a series of delta functions.
It is also a series of
It's in
delta
the frequency
functions.
domain.
For this specific case, it will be a series of delta functions. In the capital N goes to infinity. Is that, no, that is also not correct. Is it if capital N goes to infinity? So if it is a series of delta functions, then what is the period of that? Aniket? Well, you guys have done DTFT, right? So what is the DTFT of the delta function?
1.
1 from 0 to 2 pi or minus pi to pi, whatever way you want to say. So that is continuous in omega. My question is further than that, actually. Is it really filling up the entire omega axis? Is it true? Because in the discrete case, our capital N is an integer, right? So even if capital N goes to infinity, it is still an integer. Otherwise, it is not a discrete time signal. And for k and k by capital N, does it, or rather k by capital N, does it fill up the entire axis continuously? K is an integer, has to be from this definition, and this by capital N. That means no matter how n tends to infinity, how far away you are going, it is an integer. That means you are only filling up what? On this omega axis, when we go to omega, this is an integer, this is an integer.
Only rational numbers.
Only rational numbers. So is it true that omega is really continuous? That is my question, based on how you have learned to derive the um, discrete time Fourier transform, or even the Fourier transform. If you go back to the Fourier transform from the Fourier series, the same question arises. Was this covered in signals and systems, this aspect? Maybe not. Um, am I missing? I mean, am I losing you guys here, or are you with me? Unless you talk to me, I wouldn't realize. So can we say that this omega is actually only for rational values of omega? Hello. Vishwasu, Shubhadeep,
Yes, sir. I think they have to be rational.
they have to be rational. Then how do we get the frequency pi? We say angles from 0 to 2 pi, or frequencies from 0 to 2 pi, minus pi to pi. But we also talk about the frequency pi. That is, there are many other examples like this. There are many irrational numbers in between 0 to pi or 0 to 2 pi. I mean, infinite number of irrational numbers.
So are we talking about only the rational numbers from 0 to pi? Because after pi, anyway, they are going to repeat.
Now, that is again, of course, we are talking of only between 0 to 2 pi, and they are going to repeat. And if the signal is real, only 0 to pi is sufficient to describe it.
So I think we are filling up all the rational multiples of 2 pi.
We are filling all the rational multiples of 2 pi.
Like
So
k by n into 2 pi maybe.
k by n into 2 pi, rational multiples of 2 pi. So, but how do we fill up 2 pi? How do we even get to 2 pi? In this formulation, where we take capital N going to infinity. See, I'm doing these for a reason. When we do the algorithms, this will again come up for computation of DFT. So I think this is a good point to stop here today. Why don't you think about this? I mean, definitely you can look it up somewhere. Uh, I would like you to yourself think about this problem, and we will again discuss this at the beginning of Monday's lecture. Tomorrow, there is going to be a tutorial, as you know, and it will cover up to whatever we did. I will leave out the random signals tutorial part, as we have now gone into the DFT and then FFT part. So I'm not making it an assignment or anything. You think about it and let us discuss this particular issue on Monday for maybe the first 5 minutes, 10 minutes while we wait for others. But does anybody here not get the problem that we are addressing? Everybody here then gets the problem that we are addressing. Pramita,
Sir.
yeah.
Sir, is your question that we cannot get other irrational multiples of 2 pi means anything irrational multiply with 2 pi, fractional of part of 2 pi?
Yeah. Let's say the frequency is square root 2. Pramita has left as soon as I called her name. Shubhadeep, Rishabh,
Yes, sir.
is the question problem okay?
Yes, sir. Yes.
Vishwavasu,
Yes, sir.
Shrey, see, they don't even, people are not realizing that who are actually present. I have a measure of that. Sort of Sukumaran. Okay, so tomorrow there will be tutorial and there will be attendance, and then Monday we will meet again. Thank you. I'll stay for a couple of minutes in case people have questions, but you are free to leave.